Namaste. Welcome back to my channel Qubit Educational Services. In this video we are going to solve the last 6 questions from GATE XE 2007 Section A Mathematics. In the first 3 parts of this lecture series we have been solving the mathematics questions from the same paper, and today we are going to start with question number 23 and then we will go to question number 28. These questions are common data questions and linked answer questions. In the recent times, the GATE authorities have discontinued such kind of questions, but nonetheless, for practice purpose, we must solve them. So we will start with 23-24. This is a common data type, and the question is based on Fourier series. Let f be a function defined from the set of real numbers to the set of real numbers such that f of x is x squared when x is in between negative pi and positive pi, both numbers included, and f of x plus 2 pi is equal to f of x. So the fundamental period of the function is 2 pi. This is the fundamental period. Question 23. The Fourier series of the function in the closed interval negative pi to positive pi is, and we have 4 options. Observe that in all 4 options the constant part, which we denote by a naught, is the same. So a naught in all 4 cases is pi squared by 3. So while solving the problem we need not evaluate a naught separately. Question 24. The sum of the absolute values of the Fourier coefficients of f is. So here we basically want a naught plus summation mod an plus mod bn in usual notations as n runs from 1 to infinity. Next point, the function f of x is even. It is an even function, and the main interval of definition is from negative pi to positive pi, which makes the job easier. Okay, so when we have an even function defined from, let's say, negative L to positive L, then all bn's are equal to 0. We know that, right? So if you know the basic theory of Fourier series, these are some standard results from that. So the problem is essentially based on finding the correct value, or the correct expression rather, for a n. So we will start by writing down the data in usual notations. Your notation may be different based on the textbook that you are referring, but this is the notation that I have I'm used to. Okay, so the function is x squared. The lower limit, or the lower limit of the left end of the interval, I'm going to call it a. So a is negative pi, and the right end, or the upper limit, I'm going to call it as a plus 2l. So a plus 2l is pi. This makes the interval length 2l. So 2l is the interval length, and that is clearly 2 pi. So you need to subtract negative pi from positive pi. So 2l is equal to 2 pi, and therefore l is pi, and this can now help us in evaluating the expression for a n. Okay, so the formula is an is equal to 1 upon l integral from a to a plus 2l the function f of x into cos of n pi x by l dx. This is the formula. Now because n and l and pi are same, or l is equal to pi rather, n pi x upon l becomes simply cos of nx. The function is x squared, and the lower limit is a negative pi, upper limit is a plus 2l positive pi. So this is the main equation in the entire question. Now to integrate this by parts, we must know the generalized rule of integration by parts to save our time. Otherwise, as you can see, because this is x squared, you will be required to apply the integration by parts rule 2 times, as long as the derivatives of x squared don't vanish. And in examinations like these, you may not have enough time to do that. So it's better to know rules like the generalized rule of integration by parts, which I will state now. Okay, so the rule is, let's say you are integrating u into v. The rule says keep the first function as it is, you integrate the second. So subscripts mean how many times you are integrating. So u v1 minus u prime v2. Now u prime means derivative of u and v2 means integrate v 2 times, plus u double prime v3 minus and so on. Now we know that after u double prime we need not write the next expression because the third derivative of our u, that is x squared, is 0. So I've just terminated it, but the rule actually continues on and on. That is an infinite series there. So we now apply this generalized rule of integration by parts to our an expression here. Therefore, integral negative pi to positive pi x squared cos nx, where x squared is u and cos nx is v. It will be u v1. So u as it is, integral of cos nx is sin nx upon n, minus u prime v2 minus 2x into integral of sin nx upon n. Integral of sin is negative cos, so it will be negative cos nx upon n squared, plus u double prime v3. So second derivative of x squared is 2, and now if I integrate negative cos nx upon n squared again, then I will get negative sin nx upon n cube. Need to be careful here, because whenever we get two negative signs, such as in this term, we hurry and we kind of neglect the appearance of two negative signs and directly write a positive sign here, but we need this negative sign function for its further integration. Okay, lower limit is negative pi, upper limit is pi, and now we can use these standard results that sin of n pi is 0. Okay, for all values of n belonging to not only natural numbers but integers in general, keeping in mind the upper and lower limit. So from the three terms inside the bracket, the only term that is going to produce a non-zero value when substituted the limits is the middle term. It is the middle term. Okay, this term. So we will take that term further, because everything else is going to be give us 0. Okay, so now we can club negative and negative, and then we can write it as 2 by n squared, and what remains inside is x cos nx. Substitute the upper limit first in x cos nx. So pi cos n pi minus, now substitute the lower limit, negative pi cos of n into negative pi. Correct? Now because cos of negative theta is cos theta, cos of negative n pi will be the same as cos of n pi, and negative of negative pi is positive pi, so the term inside the bracket, both of them are essentially the same, so we are adding them twice. Okay, so pi into cos n pi plus pi into cos n pi, so 2 pi cos n pi, but cos of n pi is negative 1 raised to n. That is another standard result which you should remember. Cos of n pi is negative 1 raised to n. So if I take pi outside from both the terms, I will be adding negative 1 raised to n to itself. So effectively an is equal to, okay, this is not n by the way, this is the integral. We have to multiply this by a constant, that's 1 upon n. Okay, so 2 pi upon n squared into 2 times negative 1 raised to n, or 4 pi upon n squared into negative 1 raised to n. Now remember, the formula that we wrote here had this 1 over L in it. Okay, or 1 upon pi, but while integrating we are not we didn't consider it. Okay, we did not consider 1 upon pi, we just considered the integral. So don't forget to divide your an by pi, or multiply it by 1 upon pi. So this is the expression that we had got after integration, but that is not an. We have to divide this by pi, and therefore an is 4 upon n squared into negative 1 raised to n, and that gives us the answers to both of the questions, question 23 and 24. In 23 we were required to find the correct Fourier series, and we know what that is now. F of x is given by a naught plus summation as n runs from 1 to infinity an cos of n pi x by L. But we have already figured out that L is equal to pi, so it will be simply cos nx. And what is an now? For an, because this pi and this pi will get cancelled, okay, it will just be 4 into negative 1 raised to n upon n squared. So you can take 4 outside, negative 1 raised to n upon n squared cos of nx, and that is option C. That is option C. Okay, that is option C. You can check it. Pi squared by 3 plus 4 into summation negative 1 raised to n cos nx upon n squared. Now let us answer the next question, which asks us to find the sum of absolute values of the Fourier coefficients of f. Here I have used a standard result. Now sum of the absolute values of Fourier coefficients means mod of a0 plus summation n runs from 1 to infinity mod of an plus mod of bn. We already noted that bn will be 0 because the function is even. So we are now left with the sum of absolute values of an. Now what is an? Okay, ignoring for it is negative 1 raised to n upon n squared. So mod of an will be 1 over n squared into 4. Now the sum of reciprocals of squares of natural numbers is pi squared by 6. Okay, if you refer to the literature, this problem is famously called as Basel problem. It's a city in Switzerland, and I think it was first solved, as per the records, by Euler. Euler solved it, and he turned out to be, he got the result as pi squared by 6. So if you now add pi squared by 3 to 2 pi squared by 3, you will get pi squared. So that is option D. That is option D. But in case if you don't know this result that I just told you, then how are you going to find the sum of absolute values of the Fourier coefficients? For that, let us go back to option C. Okay, let us go back to option C, and we know that this is actually f of x, isn't it? This is actually f of x. Now if I substitute x as pi, then I will get f of pi. But what is this cos nx? This cos nx is negative 1 raised to n. Now negative 1 raised to n into negative 1 raised to n will be negative 1 raised to 2n. That is 1 always, because it is negative n squared raised to n. And that's exactly what you want. Pi squared by 3 plus 4 into 1 over n squared. Now earlier I told you the answer to that sum, but now we know that that sum that we are evaluating is actually f of pi. And what is f of pi? F of pi is pi squared. So that also gives you the same result, rather that is the intended way to evaluate the limit. So these are questions 23 and 24. Let us now go to 25 and 26. Question 25 and 26, these are linked answer questions. That means in order to solve 26th, you should know the solution to 25th. Let us read the common part. Let y of x be summation as n runs from 0 to infinity a n x raised to n be a solution of the differential equation d2y by dx squared plus xy equal to 0. Note that this is a linear differential equation of second order with variable coefficients, because the coefficient of y is not a constant. Question 25 is the value of a11 is 0, 1, 2, 3. 26th, the solution of the differential equation given above satisfying y of 0 is 1 and y dash of 0 equal to 0 is. So this is an initial value problem. And in 25th, they want us to determine the general solution and a part of it, and in 26th they have asked us to determine the particular solution. Now how are we going to start? Our first job here is going to be to apply the term by term differentiation theorem twice, assuming the convergence, and we have to put it in the differential equations LHS and equate it to 0. By doing that, we will get a relation between the constants or the coefficients of x raised to n terms. So let's start. This is the standard power series expansion a0 plus a1x plus a2x squared plus a3 x cube and so on. Applying term by term differentiation theorem, y prime will be derivative of a0 0, derivative of a1x is a1, derivative of a2x squared is 2a2x, derivative of a3x cube will be 3a3x squared, plus I've written one more term because here it is going to be plus a4 x raised to 4, right? So its derivative will be 4a4 x raised to 3 and so on. Now, because it is a second order derivative differential equation, we are also required to differentiate y prime now. a1's derivative 0, 2a2x's derivative is 2a2, 3a3x squared's derivative is 3 into 2 into a3x, 4a4 x raised to 3's derivative is 4 into 3 into a4 into x squared and so on. Now, let's not forget that there is this x here. So while adding the power series, we need to make sure that we multiply the power series of y or power series of y by x. Okay, so let's do it now. First of all, let's get rid of y double prime. Is the series ready for y double prime? Yes, it begins at 2a2. So 2a2 plus 3 into 2 a3x plus 4 into 3 into a4 x squared plus 5 into 4 into a5 x raised to 3 and so on. So I've written that series here. Okay, I've written that series here. Plus, now this is x into y. This is y, and note that we must multiply this by x. Otherwise, we are not solving the correct differential equation. We'll get simple harmonic motion solution there. Okay, if we don't multiply it by x. Acha. So a0 x plus a1 x squared plus a2 x cube plus a4. A0 x plus a1 x squared plus a2 x cube plus a3 x raised to 4 plus a4 x raised to 5 and so on. Okay, so that's here. Okay, and equal to 0. That is the right side. That is the right hand side. Sorry. That is the right hand side here. Correct? So once we get this, then we have almost solved the problem. Now what we need to do is we need to recognize the relationship between the coefficients. Okay. Observe that a2 is the only term which does not have a power of x with it. So a2 must be equal to 0. Okay, that is our first observation. a2 is equal to 0. Our next observation is as follows. If we now look at the next term in the left hand side of the differential equation which has a2 in it, that will turn out to be this. So after x raised to 0, we have now gone to x raised to 3. Okay, after x raised to 0, we have gone to x raised to 3, and you will also see the same pattern repeating itself. Okay, if we now go to a3, you will again find a3 in x raised to 4 term. Okay, you will find a3 again in x raised to 4 term. We know that, right? It will be a3 x raised to 4 here because we have multiplied a3x cube by x. Okay, and so on. And similarly for a4, you will find again a4 in a7 and so on. Correct? Okay. So if a2 is equal to 0, that will make a5 0. Why is that? Because a2 is only going to appear in the first term as a constant term and in as a coefficient, as a part of the coefficient of x cube. So the net coefficient of x cube is a2 plus 20 a5. But if a2 is 0, then a5 must be 0 because we don't want the trivial solution here. Okay, we want x to be non-zero. Otherwise, there is no problem and there is no question of solving the differential equation. Correct? So if a2 is 0, then a5 will be 0. Now a5 will also appear in the term with a8. So a8 and a11, all of them will be 0. So that answers the first question, that A11 is 0. A11 is 0. Okay. Now, if you want to obtain a more general equation connecting the coefficients, that relation will be this. That relation will be an plus n plus 3 into n plus 2 into an plus 3 equal to 0. Okay, this is a general relationship. If you now go to a0, then you will find the same thing here. Okay, for a0 and 3 into 2 into a3 we have x, right? So a0 plus 3 into 2 into a3, that must be equal to 0. So if I let n to be 0 here, I will get that. Okay, a0 plus 0 into 3 3, 0 into 0 plus 3 3, 0 plus 2 2, and then 0 plus 3 3 equal to 0. Okay, so a0 plus 3 into 2 a3 equal to 0, and so on. And similarly we can also get a8 and a11 equal to 0, because a2 is 0 now. If you let n equal to 2, okay, then you can prove that a5 is equal to 0. Okay, then you can prove that a5 is equal to 0. Now if you let n equal to 5, then you can prove that a8 equal to 0. And if you take n equal to 8, then you can prove that a11 is equal to 0. Okay. Okay, so such relation is called as, or is known as, a recurrence relation. Such a relation is known as a recurrence relation, because to predict the value of the next coefficient, we are using the previous coefficient's values. Correct? So a11 is done. Now we have to determine the particular solution. y0 and y-0 are given. Okay. Now if y of 0 is equal to 1, that means if I substitute x equal to 0, then y is equal to 1. Now let us see what we get if I substitute x as 0 here. Okay, what is the solution? Solution is this: y, if I substitute x equal to 0, okay, at x equal to 0, y is 1. But on the right side we have everything going to 0 except a0. a1 into 0 plus a2 into 0 squared, and so on. So that gives me the value of a0 equal to 1. Correct? The value of a0 equal to 1, and that is by no surprise, because if you read the options of question 26, the constant there, okay, is 1 itself. So a0 is equal to 1. Now from a0 equal to 1, can we find the next values? Yes, again we need to go back to this relationship. Okay, if a0 is equal to 1, if a0 is equal to 1, then we can get the following: a0 plus, okay, I've already written that there, 6 a3 equal to 0. So 1 plus 6 a3 is 0, therefore a3 will be negative 1 upon 6. a3 will be negative 1 upon 6. Okay, fine. So we can actually get the answer right there, because a3 is negative 1 upon 6, and that is there only in option D, because a3 is the coefficient of x cube. Correct? So that is option D. But let's do few more steps here. Let us also use this condition that the derivative at 0 is 0. Okay, the derivative at 0 is 0. Now the derivative term is this. This is the derivative term. Now if the derivative is 0 at x equal to 0, then that gives me a1 equal to 0 using the boundary condition. Using y dash of 0 is equal to 0. So if a1 is equal to 0, then automatically a4 will be 0. Correct? Because a1 and a4 are related to each other. How are they related to each other? a1 and a4. a1 plus 4 into 3 into a4 is equal to 0. Now if a1 is 0, then a4, it is implied that a4 is also 0. So there won't be any x raised to 4 term. And if you look at the options here, okay, option D does not have that x raised to 4 term, correct? So answer to question 26 is D, 25 is A. So what were the key parts in the solution of this linked answer questions? The key parts were, first, correctly differentiating all the terms, or term by term differentiation theorem. Then recognizing the correct recurrence relation. It takes some practice, but it will be easy given the time in the exam. Okay, so that was question number 25 and 26. Let's now solve the last pair of questions remaining, question 27 and 28. The potential ux comma y satisfies the partial differential equation second order partial derivative of u with respect to x plus second order partial derivative of u with respect to y equal to 0 in the square, 0 less than or equal to x less than or equal to y pi, and 0 less than or equal to y less than or equal to pi. Three of the edges, x equal to 0, x equal to pi, and y equal to 0 of the square are kept at 0 potential, and the edge y equal to pi is kept at non-zero potential. The potential u of x comma y is given by, and we are given 4 options. If we observe the options here, we have the circular functions sine, cos, and the hyperbolic functions sin h and cos h. Let us first draw the simple figure depicting the situation. Suppose this is our x-axis, this is our y-axis, and this is our plate of dimensions pi by pi. The bottom edge here is y equal to 0, and they are saying that y equal to 0 is at 0 potential. So I can write u of x comma 0 is equal to 0. Then if you go to the first vertical edge, they are saying x equal to 0 is also at 0 potential. So u of 0 comma y is also 0, and at x equal to pi also we have 0 potential. So u of pi comma y is also equal to 0. And the fourth edge y equal to pi is kept at non-zero potential. So all we can say right now is u of x comma pi, so it has to be either a constant or a function of x, correct? But we still don't know what that function is, and we're required to solve this partial differential equation. Now a few things about this partial differential equation. First, it is also called as Laplace's equation in 2 dimensions. Laplace's equation in 2 dimensions. Number 2, because the right side is 0, it is a steady state equation. Well, basically nothing is changing in time, so it is a steady state differential equation. And this differential equation appears quite a lot in heat transfer. When the potential represents temperature, you get such a partial differential equation. Now to solve this partial differential equation, if you know the approach, we don't solve the whole differential equation right from the beginning. We assume the solution in the form of f of x into g of y. So we make this assumption, okay, so that the differential equation, the partial differential equation, gets boiled down to 2 ordinary differential equations, one in x and the other one in y. So this is the standard procedure to solve such partial differential equations. Variable separable, you can say, the solution. Now what I have done is I have borrowed the 3 possibilities of solutions depending on the boundary conditions. I borrowed these 3 solutions from B.S. Grewal's textbook on advanced engineering mathematics. Let us first start with the third one, C9x plus C10 into C11y plus C12. Here the C's are the arbitrary constants. Now clearly we need not consider the third solution here by looking at these options, right? All these options have circular and hyperbolic functions, so let us not consider this. So it is now the question whether it is u, the first u, where you have exponential in x, or the circular functions cos and sine in x. Now if you substitute all three in the original partial differential equation, then all of them will satisfy, including the trivial solution u equal to 0. But we are also given these boundary conditions. Okay, we are given these boundary conditions, and we also need to take care of the boundary condition case, and that is actually the main part in solving any partial differential equation. We shall now show that the first one, c1 e to the power px1, it gives us a trivial solution which we don't want. So we shall first prove that it is not the solution that we want, and then we will go to the second one. Okay, so this is the first solution that we had written there. We will first pose the condition, the boundary condition, u of x comma 0 is equal to 0. U of x comma 0 equal to 0. Where is that? This one, u of x comma 0 equal to 0. Now if we substitute y as 0 here, then what will the right side be? What will be the second bracket? The second bracket will be c3 into cos of p into 0, so c3 into 1 plus c4 into sine 0 is 0. Correct? Now we don't want to touch the x terms here. So when you let this to be 0, you get c3 to be 0. So we have got c3 equal to 0. Immediately update the solution. So if c3 is gone, the second bracket will have c4 sine py in it. Okay. Now bring in the other boundary condition, u of 0 comma y equal to 0. Okay, bring in u of 0 comma y equal to 0. So this time the solution is 0 because of x being 0, not because of y. So this term is not going to participate, c4 sine of py. Okay, so if I substitute x equal to 0 here, I will get c1 into e to the power 0 plus c2 into e to the power 0. So that is e to the power 0, that is 1. So if this is equal to 0, we will get c1 plus c2 equal to 0. Clear? c1 plus c2 equal to 0. Immediately update the solution. We can now take c1 common and write c2 as negative c1. So it will be c1 e to the power px minus e to the power negative px into c4 sine of py. Observe that we may write this as 2 times sine h of px, but we will not do that. Correct? Now let us apply the third boundary condition. The third boundary condition is u of pi comma y equal to 0. The other edge, okay, in the first quadrant, the vertical edge there in the first quadrant. So if you now apply u of pi comma y equal to 0, again we are not going to depend on y, okay, because it is the x value which is giving us the 0. So if we substitute x as pi in this updated solution, we are going to get e to the power p pi minus e to the power negative p pi into c4 sine p pi into c1 equal to 0. Now we know that e to the power p pi minus e to the power negative p pi will never be 0 except for p equal to 0. But if p is 0, then of course we will get trivial solution, that is 0. So either c1 into c4 is 0 or sine of py equal to 0, but anyways this is impossible, otherwise there is no problem, there is no point in discussing the solution, which means we are getting a trivial solution if we start with exponential terms involving x and circular terms or trigonometric terms involving y. So we must now start with the second one because we already have eliminated the possibility of the third solution. Correct? So it is c5 cos px plus c6 sin px, c7 e to the power py plus c8 e to the power negative py. So it has to be hyperbolic function in y. So a is not there, and also c is not there. So it is either b or d now, because these are the only options which have hyperbolic functions involving y. Okay, so let us now see whether it is sine hyperbolic y or cos hyperbolic y. We'll start with u of 0 comma y equal to 0. U of 0 comma y equal to 0. Now this time c5 is 0. Similarly, in this case it was c3. The cos term will always go to 0, right? The cos term will always go to 0, rather its coefficient, because otherwise because cos 0 is 1, so c5 has to be 0. Immediately update the solution. U will be c6 sin px, c7 e to the power py plus c8 e to the power negative py. Now let us apply the next boundary condition, u of x comma 0 equal to 0. Now if you apply this condition, we are getting 0, we are getting u at 0 here at this boundary because of the value of y being 0. Okay, value of y being 0. Okay, so it has x has no role to play here, which means we must have c7 e to the power 0 plus c8 into e to the power 0 equal to 0. So c7 plus c8 equal to 0. Immediately update the solution, and this time take c7 common. Okay, that will bring in a negative sign instead of c8, right? Because c8 will be negative of c7. So u will be c6 c7 sin px e to the power py minus e to the power negative py. Now this in itself will tell you what option you have. Okay, it is sine of x or px and sine hyperbolic of y. So sine h. So it is D. Okay, it is D, but because this is a linked answer question, well, I mean, technically we can stop here and go to 28, but let me continue explaining how it simplifies to this by applying the further boundary condition. Acha. Now, if we apply the next one, u of pi comma y equal to 0, okay, u of pi comma y equal to 0. Now, where are we going to substitute x as pi? In this updated solution. Okay, in this updated solution. And we don't again want the trivial solution, but there is another possibility of this becoming 0 when px is actually equal to n pi, because x is pi. So p is equal to n. P is equal to n. And now if I update the solution and present it in the series solution form, because of linearity, I can write u as summation an sin nx into sin h n by. Okay, now earlier I said that we may write e to the power py minus e to the power negative py as 2 sin h of py. That's what I've done here. I've taken that 2 here and then sin h of py. Okay, and hence the correct option is D, because we when we apply the next condition, u of x comma pi not equal to 0, okay, u of x comma pi not equal to 0, we know that that is going to be the case when we substitute y as pi. Okay, we are going to get an infinite series of involving 3 terms, a constant an, a sine term and a sine hyperbolic term. Okay, now let us go to the next question. Well, we have already marked option D. Now let us go to 28. If the edge y equal to pi is kept at the potential sin x, then the potential u of x comma y is given by, and we have 4 options here. Now to begin with, let us use the equation that we have got in the 27th problem, because after all this is a linked answer type question, right? Okay, so let's use this equation now, rather this solution. So sin x is equal to, now let me expand this a bit. Well, should have written y here instead of pi, right? Oh, okay, sorry, this is boundary condition. That's right. Okay, so but now when we write the general solution, I will be writing y, should be writing, okay, that's the solution, sorry, that's the solution. Okay, now let me expand the series, because I know the Fourier series of whichever function we are going to write is a trigonometric function, so we need not evaluate the Fourier coefficient separately. Okay, so it is a1 sin x sin hy plus sin h pi plus a2 sin 2x into sin h of 2 pi. Remember, it is ny, and we are substituting, or we are using this boundary condition y equal to pi, plus a3 sin 3x sin hyperbolic 3y, and so on. But by observing this, what do we realize? We realize that a2 must be 0, a3 must be 0, and so on. But a1 must be equal to sin h of n pi raised to negative 1, or reciprocal of that. Only then sin x and sin x will match. Therefore, a1 is equal to 1 upon sin hyperbolic of pi. It's not 0, by the way. Sin pi is 0, not sin hyperbolic pi. And an is equal to 0 for all values of n greater than or equal to 2. Clear? Yes. And that gives us the final solution u of x comma y as a1 1 upon sin hyperbolic pi into, there is only one term now that is going to be there in the solution, sin x sin h y, sin x sin h y. Okay, sin x sin h y, that is option B. That is option B. So we have completed all 28 questions from the engineering mathematics section of GATE XE 2007. Please check out my other videos on engineering mathematics for GATE playlist, whose link is in the description, and of course GATE XE mathematics previous year's questions. Links to both these playlists are available in the description. If you like my videos, if my videos are helping you, then please subscribe to my channel, and you can also share my channel's link to your fellow friends and students. Thank you and all the best.